go by Eliza Gallagher and Neil Calkin. We actually have secret identities that are going to become not so secret. I'm also known as Full Deck.
I'm missing a few cards.
And together we set variant Sudoku problems. And we started setting, what, about a year and a half ago? A little bit less than that.
A little over a year.
A little over a year. And we think they're just great fun. And so how many of you have ever done any sort of classic Sudoku before? Lots of hands up. Okay, so you digits 1 through 9 in the grid. What do you think? Very classic Sudoku. Interesting, boring, some thumbs up. Anybody get tired of them? No, not at all. Oh, well, some people nodding say yes, yes. So I actually, yeah, I did. I find for me, classic Sudoku, very often either I can bust through the puzzle in no time flat, or I'm like, I don't know what to do next. This is really tough. And the techniques are typically very much the same from puzzle to puzzle. And so Neil actually started missing a few cards, actually started watching variants.
Let me tell that story.
Yes, please
It was
do. Go for it.
35 months ago to the day.
Yeah.
It was the end of spring break and the beginning of lockdown. And I had spent the week attempting to understand Zoom so that on the Monday I would be able to teach my classes with some degree of quality. I'm not sure if it was inequality or just quality, but, and I was dead tired of it. And YouTube kept recommending to me that I watch these two old white guys in Britain solve Sudoku. And I got bored with Sudoku 10 years ago. But after 15 days of being told, you should watch Cracking the Cryptic, I finally watched one. And I was hooked like that. And one of the reasons I was hooked is it wasn't just Sudoku, it was variant Sudoku as well.
And then he spent the next 18 months trying to convince me to watch some variant Sudoku, and it took longer because I wasn't seeing the pop-ups every time. It was only
And also, it was lockdown.
It was lockdown, exactly. So it was, text or an email and then silence. And once lockdown sort of started easing, the pressure intensified. So finally I gave in and said, okay, fine, I will watch one video. You get one video. And I was hooked instantaneously.
I knew exactly which video
Yes.
to play.
So, and you may notice that we are both repping the March here for Cracking the Cryptic. If you don't already know about Cracking the Cryptic, we hope that by the end of today, you will be excited to go find them and do so.
There will be a link on the pages that we hand out to a video on Cracking the Cryptic.
Yeah, well, there's a link to our website, which has, oh yes, and the video, yes, is there. So that's sort of where we started. And
How many of you know about variant Sudoku?
few hands.
Quite a lot.
Excellent.
How many of you know about Cracking the Cryptic?
Couple, no.
Oh,
Fewer hands, some nods, some head shakes. All right.
how many of you know about brimstone?
All right, well, you're going to know about all these things by the end of today. So those of you who have done some variant Sudoku, what sort of variations, what sort of constraints have you seen?
Which ones do you like?
Go ahead. Yeah.
I like killer cages.
Killer cages. Okay, so tell us briefly what killer cages are.
Basically, you get a certain cage within the Sudoku grid, and then you have to put all the digits in there, add a small number at the top of it, and give it.
Yeah, so exactly, and we'll have a puzzle that has some killer cages in it today. Other variants that you've seen, other constraints that you've seen. Ooh,
I remember that one that you were talking about at the beginning of the knight moves and the something like that.
okay, so sometimes we have, there could be chess constraints, essentially. The digits that are a chess knight's move apart can't be the same, or a king's move apart can't be the same. So,
How about arrow logic? Seen any arrows in Sudoku? Where you have a cell which is the sum of the digits along the pointy part of the arrow? In one,
I've seen it.
why don't we do an arrow problem?
Problem, yes.
Problem, not a puzzle.
Yeah.
We're gonna make a distinction between these, but I'll start.
So, since we've been setting Sudoku, we've gotten to know some of the leading lights of the community. And one of them is an Australian gentleman named Brewster. He's a computer whiz by day, and by night he solves Sudoku. And about 3 or 4 months ago, he started a new series which he calls Sudoku Problems. So not puzzles. The goal is not to place all 81 digits into the grid. It's more like a chess problem. where it's white to mate in 5 moves. You have to figure out the right sequence of things to do. And so he started out putting problems out that would help people learn techniques and tricks in solving variant Sudoku. Where are the arrow puzzles?
They're here. Sorry, I didn't realize we weren't on the screen yet. So the first one I think has arrows.
Okay. So we have 3 puzzles on the front page of this. Oh, sorry, 3 problems. And
So when I printed these, the X's were darker than they are on the copies. So there are 3 X's in this arrow problem. I'm going to pull it up on screen as well.
and maybe we can orangify those cells or something as well.
So you really only need to place digits in these 3 cells. So they do have X's on your screen, but the ones that I have up on here in orange. Now the rules, you already explained the arrow.
The rules are that the digit in the circle with an arrow coming off it, the digit in the orange circle has to be the sum of the digits on the arrow. So in this case, row 4, column 5, row 5, column 5 must add up to the digit in row 3, column 4. I'm counting the rows down from the top and the columns across from the left.
So talk to each other, see what insights you might have, and then we'll share out in a few minutes.
And we have some pencils. And
Oh, yes.
you're gonna need later.
Head up.
You don't have any pencils. So there might be some elementary mathematics that might be useful here as well.
And one of the rules for variant Sudoku is that you never place a guess. You should know exactly why a digit can be placed before you place it.
Yeah.
You should be able to articulate.
You might want to be able to put little pencil marks in to signify some information you've gathered, but you don't put a full digit in a cell until you absolutely 100% know that that digit is correct. And not only that, you can explain why it's correct.
Right.
Could be there any minute now.
Should be the same as number 5 number. So they cannot be
Yeah.
9 because here's 9. There's something and most of it is 8 and 7. But the sum of 5 numbers are is at least 10. So I think this should be 7 and 8. But here's 7, so it should be 7 and it should be 8.
Could be that, I remember.
Right, so but then you have, we don't know there, but I'm literally 1, 2, 3, 4, 5. So this
One of the nice things about the Sudoku problem series that Rem runs
or 9.
is he gives you a link to the puzzle, the problem. And he says, pause the video and go and try it yourself. And then you can come back to the video and watch his explanation of it. And if you haven't found this an easy problem, then watching the video will teach you something.
Yes.
And if you found it an easy problem, it might well be because you watched some of Brewster's previous problems and he taught you some techniques.
And to clarify and also to give credit where credit is due, this is not a problem that we set. This is a problem that Brewster set. The video link that we've got there, the YouTube video, is to Brewster's channel and his explanation of this problem.
And please like and subscribe.
Yes. He's well deserving.
Yes.
But let's hear some reasoning. So what observations can you make? We've made some progress with this.
First of all, how many can we solve it?
Good answer.
Good.
It's less than 7.
So
So why don't we do this? Those of you who have solved it, perhaps partner up with those around you and talk those around you through some insights on this problem. So if you haven't solved it yet, look for somebody who has.
So I'm thinking. That must be
Okay, so a big part of what we like about the variance Sudoku community is the fact that at the heart of a lot of the interactions that happen is mathematical reasoning and mathematical communication. So would one of you talk us through an insight that you had or your reasoning for this problem? Yeah.
So like the one thing that I immediately noticed was the upper bound for the top 2 squares to fill in is 15 in total. And the lower bound for the 5 squares at the bottom would also be 15.
Okay, so tell us a little bit more about that.
So
These two, so let's go ahead. I'm going to turn on for here row and column labeling, and in Sudoku we do it a little bit perhaps backwards from what we might hope from coordinate axes, but we number the rows from top to bottom and the columns from left to right. So we can think about, yeah, but we can, yes, that's fine, but for those of you who think in matrices, that's great. So we can think about these as being row 3, columns 4 and 5. So if we talk about it using those names, it'll make it easier for folks to follow. Okay. So tell me about those two cells.
So row 3, columns 4 and 5, they obviously can't be higher than 9.
Okay.
So that was sort of like the first thing you noticed, and then just as like some basic stuff for the like row 4 or 5 in that like little section, and then row 6, columns 4 and 5, or just column 5 actually.
Okay.
It was using just 1, 2, 3, and 4. The lowest possible number you would get would be 15.
So
I must have misheard what you said.
1, 2, 3, 4, and 5.
1, 2, 3, 4, 5. Okay. Okay.
And then that's equal to like 8 plus 7, which would be the numbers at the top.
Yeah, and that's exactly the reasoning that it gets developed in this problem. These 5 cells combined have to be at least 15. Those 2 cells combined are at most 15. So, boom, that's your only possibility. So one of these is 7 and one is 8. How do we decide which is which?
Well, yeah.
Now we have to go back, and actually, it turns out variant Sudoku, sometimes the hardest thing to remember is to do basic Sudoku. So there is a 7 in this column, so we know this one has to be the 8.
And sometimes the given digits in Sudoku get referred to by players as invisible digits, invisible given digits.
Now we have one more digit in place. Yeah,
It just has to be 7 because there has to be 7 in the middle block with the other 2 like columns.
Okay.
4 and 5 or 6.
okay, you have to have a 7 in box 5, which is the middle box. These columns are taken up. So tell me why the 7 has to be in the orange cell.
Well, because for like, if you're adding all of them together and you have 3 for 8, if it's 7, like if 7's in one of the other 2 rows, it just doesn't make sense because all it's left to add up is 1 and you can't add 1 twice.
There you go. You have to have 7 with a 1 and a 0 to get there. So yeah, boom.
0 is not a legitimate Sudoku digit most of the time.
Yes. And then if you go to any of these YouTube links and you follow the puzzle, the problem link from there, you do get a nice solution checker popping up. So
The solution is
the
correct.
solution's correct. Yeah. But that communication of why it happens, that's one of the things that makes all of this incredibly powerful to us as
Mathematics educators.
and yes, yes, all of that. So we have another one for you here. Have any of you ever seen Venn band lines before? One hand.
Hmm. The red band lines are usually purple. And the indication that is made when you put a purple line like this down is that it has a set of contiguous digits. It could be 1, 2, 3, it could be 2, 3, 4, 3, 4, 5, 4, 5, 6, but depending on the length of the line. It doesn't matter what order the digits are written down in, but they have to be contiguous, so no gaps and no repeats. So the 5 digits here could be 1, 2, 3, 4, 5. It could be 2, 3, 4, 5, 6, up to 5, 6, 7, 8, 9.
And again, we only need to place digits on the X's. Just those 3 cells. This puzzle was set by another friend of ours, Dumdiat.
Not some idiot,
Yeah. Definitely not dumb idiot, Dumdiat.
a smart person.
Yes, very much. And so we do want to give credit to Dumdiat for setting this problem. So take a minute, talk about it, see what you can figure out.
Good.
Process this one.
I have a, this, someone off, out of the fix. So people think. I guess I feel like, and
Yeah, so. Yeah, so you look at these cases.
I'll just say
That looking into this combine. You'll see
Okay, anybody figure this one out? Okay, let's go and do this first. I'm gonna talk through some of the key logical points.
Me? So in row 6, considering the fact that you already have 4 in box. You know that the purple red band line, red band line has to be 5, 6, 7, 8, 9.
Yeah.
Because it's the only set of 5 you have, so that leaves 1, 2, 3, and 4. Because you already have a 4 there, so it has, you need to place 1, 2, 3. Since 2 is already in column 6, the 2 has to be placed. Row 6, sorry. It has to be placed in the row 5, column 5. And then because the 1 is in column 6, it has to be placed in row 6, column 4, which leaves the 3 to be placed in the last one.
Good. You were faster with that puzzle than the other one. Yeah, the intuition that the red band line is constrained by the fact that there is a moderately high low digit in the cell means that you're forced to put the digits on here, and then the placement of the digits, the other digits around the grid, provide you with the remaining information you need. Okay, I'm going to bring up the.
Yeah, let's combine these.
Oh, what? Arrows and red band?
Yeah. And radius. So this is the third one on the sheet. And so it is a puzzle that was set by 3 people working together. Raoul Palmer,
In Germany?
I think in Germany.
Mhm.
Zion Risk, who is in Texas, and Crusader 175, who is in, I think, Singapore.
Indonesia, maybe? Malaysia?
Yeah, so the variant Sudoku community is very international, lots of online interactions. So this problem was built by 3 people on 3 different continents working together to set it. And it uses the 2 constraints that you've already seen, arrows and red band lines. And this time you only need to place 2 digits. Those 2.
I have a question.
Yes.
So when you say consecutive order, do you have to go 1 to 9?
Oh, for this, it is 9 digits and they must form a contiguous set of digits. So it must be all the digits 1 through 9 in some order. They don't
Yeah,
have.
they don't have to go 1, 2, 3, 4, 5, 6.
So it could be 9, 8, 7, 6, 5, 4, 3, 2, 1.
Okay, can you do 1 after 9 and starting? from-
Yeah, you can do
Yeah.
3, 7, 2, 8, 5, and whatever order you can have them non-repeating and they're all consecutive. Make this a set, so.
When you were saying that they didn't have to be ordered, they could be 1, 5, 7.
Yes.
So long as you have all 9 digits.
Yeah.
Now, I don't know, it should be woman.
No,
Okay,
not yet.
okay. What can we be woman about?
Oh, I don't know what should be important about. I'm so sure. I know nothing.
So there doesn't have to be a pattern for the line.
No, that red band line, it contains 9 cells, so it has to be the digits 1 through 9, but you don't know anything else about it other than.
In fact, you don't need to know anything else about it for this problem.
Get the numbers on.
So that's right. You
You
don't.
only need to get the orange cells
Yep.
numbers.
Yep.
It's guess right.
Yep, then, only 80. You can buy them all. Actually,
It's
fewer
only
than
72
81, they
guesses.
have to be distinct.
Yeah, so, yeah,
So only 72 guesses.
yeah, so if you get this, yeah.
You could probably do that in a seminar.
Yeah. That's,
So the reason I said should we warn them, this is actually quite a tricky problem,
Yeah.
unless you know some Sudoku theory. Wait, what?
theory of Sudoku.
Theory? Sudoku
Surely
theory?
not.
A Sudoku theorem, in fact.
Yes.
In this case, it gets called Ard's theorem.
After Odd van der Wetering.
Ard van der Wetering is a 77, 78-year-old Dutchman who is one of the most brilliant Sudoku and puzzle constructors in the world. And he discovered a rather beautiful result.
And this is about the geometry of the grid. And this result actually doesn't have anything to do with the constraints.
In fact, do we have a blank grid?
We
that
do have a blank grid. I have a blank grid, and we're gonna start using some colors. How many of you, we've got to ask about Scrabble already.
Yeah.
How many of you have played Scrabble before? Okay, so you know, there's not all the hands, well, that's fine. Imagine that you have a set of tiles. Yes, tiles with the digits the numbers 1 through 9 on them.
Lots and lots of copies of each number.
Yes, as many copies as you need. And they're in different colors. You got 2 sets of tiles. You got some blue tiles, you got some yellow
And
tiles.
I've got a nice little fabric bag here.
Do you?
In fact, I've got 2 of them. I'm going to put, what color tiles are we going to use?
Let's use blue and yellow.
Okay, so I'm going to have blue tiles in this bag and yellow tiles in this bag, and I'm going to keep track of what tiles I've got. Okay, blue in my left hand, yellow in my right. Right is longer than left, yellow is longer than blue. That's how I'll remember that.
You want to turn some tiles blue and yellow up there?
Yeah. So let's turn tiles on the left blue. These, you think?
Sure.
You want to turn some yellow?
Turn some yellow. I want to stay as far away from those blue tiles as I can. So I'm gonna pick those to be yellow.
Okay. Can you tell me anything about the blue tiles and the yellow tiles they might have in common?
That's a tough question. Maybe it would help if we colored some more things.
It might. You want to do this?
Yeah, so why don't we add, let's in your bag of blue tiles. Give you some more tiles.
Now can you tell me anything about the tiles I've got in my blue bag?
I can tell you exactly what you've got in your set of blue tiles there. I see that you've got a copy of the digits 1 through 9. And a second copy of the digits 1 through 9. And a third copy of the digits 1 through 9, a fourth copy, and a fifth copy. So I'm pretty sure that in your bag of blue tiles, you have 5 of each digit. Yeah?
It's in yellow, but in blue.
Well, I want more tiles too. So I'm going to take those tiles. I'm going to take, in fact, I'm going to get rid of your blue tiles for just a moment. Just so that we can see what I've got, and we'll put them back in a minute. We know what Neil's tiles are. Those are my tiles. I've got those yellow tiles. So what do I have? I've got 4 copies of the digits 1 through 9. I'm going to put Neil's tiles back now. So he has 5 copies of the digits 1 through 9. I have 4 copies of the digits 1 through 9. And we've got some overlap. This
I
time,
don't mind that tile. I'm going to take it out of my blue
well, then
bag.
I better take it out of my yellow bag as well. Now neither of us has that tile.
And the one next to it, to the left of it.
That one too? We're gonna get rid of this one too? Okay,
Yeah,
fine.
both of us.
Both of us.
And how about the bottom left one that is?
Oh, actually, I hate that tile as well. For both of us.
All of those doubly flash tiles.
Yeah, I don't want to
They're
have the
all
same
in those
tiles.
bags, right? So we can just pull them out.
We're getting rid of exactly the same tiles. So now what do we have?
So I'm going to call the set I took out S.
Well, I took out S2.
Wait, so I started with one more copy of 1 through 9 than you did.
Yep.
And then we kept taking out the same tiles.
Yeah,
So I must still have one more copy of 1 through 9 than you do.
yeah. I think you're right. I think you do. I think you've got exactly one more copy of 1 through 9 than I do. I wonder how that might relate.
Can we count the cells and see if that seems realistic? 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5, 5 times 5 is 25. 1, 2, 3, 4 times 1, 2, 3, 4 is 16. Subtract 16 from 25.
Yeah, 9 more
Put 3, 4,
tiles.
5 triangle. We get 9. Yeah, makes sense number wise, right?
It does.
But is there a set of tiles we could remove that would make them have the same?
Well,
number?
you know, I think I've got a whole set of the digits 1 through 9 right there. And you've got a whole set of the digits 1 through 9 right there. What if we get rid of those? Can we agree on that?
Well, I've still got an extra set of 1 through 9 than you do.
Yeah, okay, well. At that point, so what we've said here, so odds theorem, and I think out this extra set because that'll make it apply more to the specific problem. Well, let's go back to what we had just a moment ago. When you're at this point, it turns out that for any Sudoku grid, whether you've got extra constraints in play or not, the digits in that yellow region, the lower, and I can't do left and right, the lower right will be, well, I'm sorry, the blue digits, the ones in the upper left, will be exactly the same as the yellow digits plus an extra copy of the digits 1 through 9.
No
Pick
matter
up
how you
any,
validly
yep.
fill out the Sudoku grid.
pick up any Sudoku problem from the newspaper. If you've got a correct solution, check it. The 25 blue digits will be exactly the same as the 16 yellow digits plus an extra copy of 1 through 9.
And in fact, if you were to just take these digits and pull them out, now the blue would have exactly the same digits as the yellow.
Yep.
Because I got rid of a full set of the digits 1 through 9. That was the only difference between them.
Yeah.
Okay.
This type of geometric argument of looking at where cells agree and don't agree and overlap has come to be known by the very unfortunate name in the Sudoku community as set.
This was invented by a friend of ours, Philip Newman,
Yes.
as a name for it. And unfortunately, it's called set theory. What set stands for is set equivalent theory.
Yes.
So set is set equivalent theory,
Yes.
which is
Set theory
equivalent
is.
equivalent theory.
Philip is a mathematician. He did name this with a recursive name as a joke, and it did take off in the community. So set is set equivalence theory and gives us all.
It's
this.
like the Tartar pits.
Yes.
The La Brea tar pits means the Tartar pits when you translate the
And
Spanish.
that's kind of interesting, right? Because the yellow one has to have a single set of 1 through 9. It can't have
Correct.
extra, which means that strange blue one has to have a 1 through 9 set.
Yeah.
That's interesting.
Yeah.
In fact, should we go back to the other puzzle now?
Yeah, let's go back
Problem?
to this problem because now it's flipped on the grid, but we've got basically that same thing. Here are what's left of the yellow after we take out the extra box. And here's what's left of the blue after we take out corner box. So the blue has to be exactly the yellow plus a set of the digits 1 through 9.
But
But what's happening on that red man line?
that's the set of the digits 1
It's
through
a set of
9.
the digits 1 through 9. So let's get rid of that.
And now the blue and the yellow contain exactly the same digits.
Yeah. This is why we like variant Sudoku. This is why we like Sudoku. This is why we like the variant Sudoku community. These are the sorts of conversations that are happening about, oh, what can we do to make life interesting? So,
And the comments in the videos, people were saying, wait, does this always have to be true?
can you prove
Yeah,
that?
can you prove it?
And this is from non-mathematicians, so it makes us very happy.
Yes.
So rather than finish out this problem, we will leave it to you to go watch the video and see how it goes from here. But this is the fundamental piece of logic that's behind making this problem solvable.
And some of you may now be able to figure it out.
Yeah. But we're going to shift gears a little bit. Because we have another handout for you. And now we're going to start playing with colors.
You all brought your crayons, right? Oh, no, we gave you.
So we're giving you a blank grid.
And you'll need 3 different colors.
We'll need 3 colors. Pick 3 colors. Pick red, blue, and yellow.
Yeah, when we say hit, pick red, blue, and yellow.
1, 2. No, but they don't need it. They
You
need
need
anywhere.
Pick one blue. and
Just 1, 2, 9, 1.
Pick one red, one blue, and one yellow. Wait, I think that's a good start. Red, blue, and yellow?
Yes.
Okay.
Anybody else need color control?
We have lots.
Okay, all right. So, take a look at all. That's it.
No problem. You don't have
What? The task before you is to explore. What you're gonna explore though is like, we want you to think of the digits 1 through 9 being subdivided into 3 groups. Each group's gonna have 3 digits in it. We don't care which 3 it is. You decide in your head that 1, 2, and 3 go together, and 4, 8, and 9 go together, and 5, 6, and 7 go together. We don't care. 3 groups. A different color associated with each group. You're not gonna write any numbers in this group. We are putting a constraint on the diagonals of this grid. So just to be clear, diagonals would be things like
So not just the main diagonal, not just the positive diagonal or the negative diagonal, but what length diagonal?
that's a cell, that's a diagonal of length 6. That one's gonna be subject to the constraint we're imposing. Anything shorter isn't, but anything that is length 6, length 7, length 8, or length 9, and there are 2 of length 9, 2 diagonals of length 9. All of those are going to be subject to this constraint. They have to be colored. They have to be cyclic. The coloring has to be cyclic using those 3 colors of red, blue, and yellow. The period could be 1, meaning it's all the same color, or it could be period 3, meaning you cycle through those same 3 colors in order along the diagonal. And we want you to figure out as much as you possibly can about coloring this grid under that constraint. So talking and playing and coloring and figuring out what you can figure out about how you can color this grid.
Period. Color one of these diagonals with polychromatic colors. So let's pick this one. So this is a monochromatic diagonal.
So like 3 of the numbers are.
No.
3 of the numbers are another.
You get kicked off.
It's just a ring. It says.
This is a monochromatic blue diagonal. Period of 1, which means every cell, one step you take, you have to be very outside. And this one I'm going to color in a polychromatic way, and I can't just click all of those at once and color them at once the way I did with blue, but I'm going to say, let's make this one red. And this one yellow. So this one has to be period 3, so this one has to be back to blue. This one, 1, 2, 3, has to be yellow. This one has to be 1, 2, 3, red. This one has to be blue again, and this one has to be yellow. So is it clear what we mean by polychromatic? And we're insisting that every diagonal of length 6, 7, or 8, or 9 has to be one of those two types.
We haven't said anything about shorter diagonals. Nothing imposed on by us on those diagonals of length 5, 4, 3, 2, or whatever. But now playing.
So there are some cheap deductions you can make here. Make some.
Yeah, I'm trying to stare at it.
Oh, I need to thank you for that. Sorry, chat people, I forgot to pop this one in for you. It's coming. And.
That would be fine. I guess I'll.
Yet, but
They need it anyway, so.
I'll need it in a few minutes.
These are trends.
It's interesting.
So some of you are still just sort of sitting there staring at the grid and haven't put anything. I will say, go ahead and color something. The worst that can happen is you come get a blank grid. But it's going to be really hard to think this through without committing to something on the grid and then see where
Does
it
anyone
goes.
have a favorite cell in the grid?
I like the middle grid.
You like the middle? Yeah. Well, I like the grid, but what's your favorite color of these things?
Probably red.
Red, okay, well, let's go ahead. Without loss of generality.
A phrase that mathematicians love.
We can assume that row 5 column 5 is red.
Yeah, the red colors all correspond to one set of 3 digits.
Yes.
So how many cells in box 5 can be red? And how many can be blue? And how many can be yellow? In fact, you must have 3 of each of them. That'll come in handy. Hey, yeah. Yes.
Yeah.
Can I have another case?
You're the first.
Thank you.
You've got something interesting happening on yours. What do you tell us what you've got there? You've got something there.
The middle block on the top left, right, and bottom boxes all have to be the same color.
Why?
Because they differ by 3, yeah, so those would have to be red. They're 3 blocks away on the diagonal from the middle square there.
How can you be so confident that they're red? We don't even know whether they're monochromatic or polychromatic.
Because whether it's 1 period or 3 period, 3 steps away is the same color.
Ah,
3 copies of a single period it's periodic at that distance. One copy of the length 3 period is periodic at that distance, so we can color those cells.
So that center red cell is now propagating outward. 3 away along the diagonals. If the diagonal is long enough,
Yeah.
we'll repeat the color.
And those diagonals are both length 9.
So we're good. So I wonder, could both of those could both of the long diagonals be all red?
No. No,
Why not?
because it would mean you'd have 5 of the same set of 3 numbers in the middle.
Yeah, if we try to make both of these long diagonals all red, we would have 5 red cells in the center. So that's not gonna work. So at least one of them is polychromatic.
Can we pick one without loss of generality and pick a coloring for it, maybe?
Yeah, is somebody out there pick?
Doing the positive slope one.
Positive slope, you want that one to be polychromatic?
I chose monochromatic for that one.
Oh, well, I'm not convinced there is a monochromatic one. I do know there's a polychromatic one.
Oh,
Because they can't both be monochromatic, but I'm not yet convinced that there is a monochromatic one. So let's pick one to be polychromatic, since we know there is one.
the negatives.
The negative's color point? Okay. So,
Which color is this one?
yeah, what color is that?
Out of yellow and blue.
Yeah,
Let's do.
blue. Okay,
What's the other color there?
and what goes here then?
Yellow.
It's gotta go yellow in order to be periodic. Now, does it matter? Does it matter that we let Alec pick the direction of which one is polychromatic? Especially on this. May I borrow this for a moment?
It actually does.
So if you like that orientation, take your paper and you will now have the same diagonal working.
So other than isomorphism and other definitions cloud, nobody else understands. Without lots of generality,
Yeah.
we let out.
And we also let Alec pick the colors, again, without loss of generality, because you can just map red to blue or blue to yellow as you need to. So what else can we do now? Extend the pattern. So to be period 3, I'm 3 away from yellow, I better get to yellow. 3 away from red, I got to red, 3 away from blue, I got to blue. I can go the other direction too. That one better be blue and that one better be yellow. Anything else I can do?
Along the length 7 one there, where the blue is,
Good blue?
yeah, you can extend this way since that's length 7.
Ah, so that is a length 7 diagonal. So, and you're saying we can extend, does that mean they're all blue?
Not necessarily,
Okay, so what can we say?
the ones on the end.
The ones that are 3 away.
Maybe turn row labeling on.
Yeah. Okay. Get another one here? Yeah. Fair enough. What else can we do? Anything at this point?
Same with the yellow diagonal, 6, 6.
Okay, same with this yellow. Check the length of the diagonal. It's length 7, so it is subject to our constraint. So 3 away. We get yellows. And now we stare quietly at the grid for a few minutes to see what else we can see. Or not quietly, it's also good to talk to each other. About row 4, column 6. And what color row 4, column 6 could be? It could be either red or blue or yellow, right?
Not allowed to use purple.
But it's on a couple of long diagonals.
Laura,
Isn't it just red?
That'd be red.
why?
Why? Well,
Okay, so you have like the poly or whatever on the. So then, in order for like it to work throughout all of them, it has to have like the monographic. So if you have.
Why?
I don't know what I'm saying. It has to have the monochromatic for the other ones, or else the pattern won't work later on. So if you
Why?
have like the positive slope of the like middle line, all be monochromatic, and then like for the like three above, the three below also red.
I'm gonna be that person on the internet.
Yeah.
He said, I'm not following your argument. I don't see why it's gonna be monochromatic.
Well, because that's the only way for it to work across all of the.
Why?
Don't call me out like this.
You said the above and the below.
Well, okay. How am I supposed to explain this?
I would say suppose it's not red. And try the other colors. And see what happens.
And I would also simultaneously point out that we have this sort of 5 spots on a die thing going on, right? So we've got the blues that are 3 away along these diagonals, and the yellows that are 3 away. Where are row 4, column 6's friends?
It can't be blue, I don't think.
Well, that's what Laura's claiming,
Yeah.
and you've explained it almost as well.
If it is blue, you have in row 1, you're gonna have to have a blue in column 3 and 9s. And you'll have 4 blues along that, but they're only 3 digits.
Those 3 have to be the same color,
Same issue.
And it can't be blue.
and they can't be blue because that would put too many blues in row 1.
You've got the same issue with yellow if you look at the right column.
There's another of row 4, column 6's friends, and column 9, that would make too many yellows.
See, I saw this way back whenever I said they're monochromatic, right?
But you see how that's a clear explanation of why it has to be monochromatic.
Yes, mathematical reasoning and communication.
So
Those are all red.
we can cover them all at once. Oh. Well, what does that mean for
What
the
did that give us?
positive diagonal?
Does this have to be banded?
We'll find out, won't we?
That means the positive slope has to be all red.
These are all red. We can no longer be period 3 once we've got 2 of the same color right next to each other. Those are red. Okay. Wow.
And
What about row 4, column 5? Can that be red?
Why not? You're shaking head.
Cause I would put 4.
Yeah, we've already got the
Yeah,
red.
already pulled it out. Too many red. So yep.
So either blue or yellow.
Let's look at its friends. Same trick. 3 away, because all of these diagonals are long enough to satisfy that condition. To need to meet that condition. What does that give us?
it has to be yellow,
Why?
because if it was blue, then at the top you have 4 blues, which you can't have.
We already ruled out red. Those are yellow. What about row 5, column 4? Can't be red. Friends? Here and here and here and here.
Has to be yellow.
Gotta be yellow.
Can't be blue because it would give 4 blues in column 1.
Oh, and now look. We've got a long diagonal. And 2 in a row that are yellow, they better all be yellow.
I swear.
What's the rest of box 5?
Blue, blue,
Whoa, what does that tell you about that diagonal?
blue.
That whole diagonal is blue.
And this is all just coming into place now.
It is. Gosh,
Anything else we can get? Oh,
what about that diagonal right there? It's link 6, and it's got 2 different colors on it. It better be polychromatic. There's a blue. There's a red. There's a red. There's a yellow. Oh, can we say something about that cell now? I got 3 yellows on that diagonal.
You can,
Wait, no,
you
that's,
can,
Only for them 6.
Oh. Yeah, I don't get to make that conclusion because my condition is only for diagonal for 6 or longer. So I can't apply it here. That's really very disappointing. All right. Where are we? We've got to wrap up. It's 6 o'clock,
yeah, almost.
almost.
So. Any others that we can see, like this one? Polychromatic. And this one. Those are not distant 3 apart, so it must be
No,
monochromatic.
it must be.
I'm just picking the ones I can see. These red
Yeah.
ones here are not 3 apart. So, and it is length 6,
So
so they
they're
must be
all
red.
red. Oh, and this one is length 6. And got lots of colors on it, so it better be polychromatic. And these are just filling right in. What are we gonna do though? About, oh, I don't know, this one right here. Can we make any conclusions about that one?
Not yet.
I think we might be able to. Could it possibly be polychromatic?
No,
Why not?
I would put 4 reds in box 4.
If it were polychromatic, one of those 2 would be red. That'd be too much. So yeah, these have to be blue. So,
Mark, you asked if it.
Mark left.
Oh.
But we will go ahead and fill out with this same reasoning, and it does in fact turn out to be quite lovely. That better be blue.
Do indeed get this banding of the grid. And as a neat exercise, we're going to leave you with a question. What happens if you don't insist on diagonals of length 6, 7, 8, 9, but only diagonals of length 7, 8, 9? Can you prove the same thing?
And we will leave that as an exercise, but we also have a puzzle for you to take off the door with you. It uses a similar condition, but actually restricting it to only length 7 or higher, and assigning those digits to the 3 groups using residues modulo 3.
So the mathematics
The
behind it.
mathematics. They're also on here on this fact sheet are a link to our website where there's a bunch of puzzles and a link to where the puzzle that is here gets solved on Calkin and Eliza. On the back of the first set of problems we gave you is a flyer for Maths Jam. Maths Jam is an international social gathering for people who like recreational math. It's the next to last Tuesday of every month, so next Tuesday, 7 p.m. We are getting one in Clemson just up and running. This will be our 2nd meeting ever. And we meet at Brews on the Square in Pendleton, which also has coffee.
So
So
if you're under 21
Or
or
just
don't
don't
want to
drink.
consume beer.
Yeah.
Come out.
yep.
If you're over 21 or do want to consume beer or don't want to consume beer, come out.
Yeah.
We will be gathering to do some puzzles. Some of them may be sudoku, some of them may be physical puzzles.
Yeah.
Some of them may be riddles or math jokes.
Yeah.
Depends on who turns out and what they bring.
Some of our undergraduates in a different class have believed that they have a puzzle that with which they can stump one or both of us, so
Probably
that
me.
would be entertaining. So yeah, we hope you'll come. If you don't, we'll this month, then a different month, and do some Sudoku. Stick around if you want to talk to us. We will talk about Sudoku forever. Otherwise, have a great evening.
Yeah.
So,
Questions?
sorry, we spent the whole time.
Our website is named after our setting names. It is missingdeck.net because it's full deck and I'm missing a few cards.
Any questions out there or? Actually, I do have I have like an old school skate. I've wondered this, I don't really know the answer to it. So, you know, you get the Sudokus in the newspaper, and usually as the week goes on, they get harder. And so, how are those things constructed so that there is a solution and it's unique, right?
It's a special technique called the DFI method,
Mhm.
brute force and ignorance.
But because the thing that occurs to me is, you know, when you put these together, I mean, I can't just put a Sudoku thing and just put a 4 somewhere and say, go ahead and solve it, right? Because, I mean, you could, but you
have the
certainly
right
would,
software.
yeah, you would, well, the solution almost surely would not be unique, right?
So this is a great question. In order to have a unique solution, you have to have in a regular Sudoku, you have to have at least 17 given digits. That's the absolute minimum. But just because you have 17 given digits does not mean it's solvable.
Right.
And just because you have a bunch more than 17 digits does not mean it's solvable. And it does not mean it's easier than one with 17 given digits. In fact,
Usually 17 given digit Sudoku puzzles are considerably easier than a carefully constructed one with more digits, because every single digit has to do so much work to drive forward the uniqueness of the solution. So
there are some beautiful examples, in particular constructed by Philip Newman, who we mentioned earlier, in which he has a puzzle with 17 digits, which is easy.
Yeah.
And he has a puzzle with, what is it, 53 digits?
yeah, that
Which is
almost
diabolical.
impossible. Yeah, it is. You only have to place 28 digits, but getting them is just gonna take hours.
Or we've all fallen into that trap, right?
Yeah.
You see, it's like, oh yeah, this is easy, it's
Yeah.
mostly full, right? And
Yeah.
it just doesn't burn out.
Newspaper Sudokus tend to use number of digits, number of given digits as a proxy for how difficult it is.
Yeah.
Not a good proxy.
No.
And there isn't usually a flow to the solve of the puzzle. Whereas if you find somebody who's handcrafting a Sudoku, we like to think that the puzzles on our website are carefully handcrafted with computer assistance, don't get me wrong. But we have ideas for how to flow around the puzzle and how the logic should interact. And that's the beautiful thing about variant Sudoku, is it introduces new logical tools. The odds theorem and Phistomefel's theorem, which has a similar flavor to
Which we
odds
didn't
theorem,
talk about today, but
they apply to all valid Sudoku grids. But there are much more techniques. A simple example is the arrows in the very first problem. These 2 cells had to add to the same as these 5 cells. These had to be at most 15, these had to be at least 15, therefore they were both 15. This couldn't be 6, 9, so it had to be 7, 8. That's a 7, that's a 7, that's an 8. Oh, 7 can't go on its own arrow.
Yeah.
So it must be here.
yeah. So these interactions really just make it so much more fun and so much more of a logical flow. If any of you are interested in learning to set variant Sudoku puzzles, we have a creative inquiry that is started this semester and will be continuing in the fall. Feel free to come talk to us about it. If you're in the honors college, we'll be offering an honors seminar on math puzzles in the fall as well.
And there's an honors version of the CI and a non-honors version of the CI. So whether you're in the honors college or not, you can come out and
And if you're a graduate student who wishes you could take a CI course, come talk to us.
figure it out.
We'll figure something out.
Sounds like something fun to get ChatGPT to screw up.
We'll get us started.
So one of my students last semester with the ChatGPT within minutes of it coming out. A very strong undergraduate freshman in computer science major. Who's not here today.
No, he's not. We're gonna yell at him on Monday.
Yeah. Anyway, he prompted ChatGPT to explain the rules of variant Sudoku, and he did a reasonably good job, and he tried to get it to solve cryptic crossword clues, and it was spectacular fail time.
Yes.
Yeah. Legacy rhymes with galley.
If pronounced with a British accent.
Actually, earlier this semester, somebody turned me on to it, and I actually proved a theorem. I solved an old problem. And I came into work the next day and asked ChatGPT to do it, and it messed it up.
Oh, yeah.
So my favorite interaction though was asking it, getting Nathan to ask it to describe 2 evil math professors named Fulldeck and missing a few cards who in their spare time set evil Sudoku puzzles.
Yeah.
It took a lot of massaging, but it came up with a lovely little story about these.
A little short story about their evil ways and being eventually defeated by the students. So.
Any other questions, comments? All right, everybody out there and in here, have a great weekend. Next week is gonna be a little bit different, I believe, because we got the Math for All conference. I'm gonna send around an announcement about that. So it won't take place really here. It's over at the, I think it's Hendricks. But anyway, I'll send that around in the announcement. There's a number of good talks, so I would. Maybe what?
Yeah.
Oh, it may be why. I've gone and forgotten. I thought it was Hendricks, but I could be mistaken. I'm not sure. So I'll let you know about that, but there'll be some interesting talks. And if you're a regular at Mac Club, you don't really have to register, although you certainly can.
Please do, because it helps them get accurate numbers, and that will help with funding in the future.
Right,
So
right.
please register it free.
Yeah.
And we love having names and faces.
There will be a pizza and talk at about this time next week, so I'll send that. So everybody have a good weekend.